Welcome to the Explainer. I am so incredibly excited you're here because today we're going to do something, well, a little bit different. We're taking the IGCSE Trigonometry syllabus, specifically chapters 28 through 30, so your core and extended topics, and we're transforming them from just a dry list of abstract rules into a pretty epic journey. Seriously, let's dive right into this. We are going to span everything from the literal heights of modern space exploration down to the surprisingly dramatic and honestly kind of toxic historic rivalries of the Swiss mathematicians who actually built these formulas. Now, what's really fascinating here is how this grounds everything we're about to learn. Just take a look at this stunning satellite imagery. It's so easy to look at a math exam paper and think trigonometry is just about triangles drawn on a flat page. But the exact same 3D trigonometry that keeps a spacecraft properly oriented in the vacuum of space, that's exactly what you have to master at the peak of the extended syllabus. When you're calculating these angles, you're not just doing math, you are literally speaking the language of orbital mechanics. How cool is that? So, our agenda for today covers 4 distinct parts. First up, the scope of trigonometry. Second, essential trigonometric rules. Third, the genius of Euler. And finally, the Bernoulli family drama. Okay, it's section 1, the scope of trigonometry, breaking down the syllabus. The syllabus actually does a really nice job of cleanly separating foundational skills from those highly complex extended topics, running all the way from section E6.1 through E6.5. It kicks off with the core basics, things like interpreting 3-figure bearings in E6.1, and then, while it steadily ramps up the difficulty, you're moving from flat 2-dimensional shapes right into the deep end of 3D mathematical problem solving. Think of your progression here like climbing a staircase with 4 main steps. First off, you'll tackle 2D right-angled triangles. Next, you step up to actually graphing trigonometric functions and recognizing their properties. From there, you conquer the rules that apply to literally any triangle, even if there's no right angle in sight. And then, finally, you reach the top step, mastering 3-dimensional planes. Moving on to section 2, essential trigonometric rules, the tools of the trade. Right, so under section E6.2, you absolutely must master the foundational ratios. We're talking about applying Pythagoras' theorem, along with your trusty sine, cosine, and tangent ratios for acute angles. You'll use these to hunt down missing sides or angles in right-angle triangles. And I love this part, because it brilliantly illustrates how math models the real world. You're going to heavily apply these to solve 2D problems involving angles of elevation, so looking up, and angles of depression, looking down. Oh, and you're also required to extend your sine and cosine values to angles between 90 and 180 degrees, so keep that in mind. Now, before we leave E6.2, there is one absolutely crucial geometric rule explicitly highlighted in the syllabus. It's this: the perpendicular distance from a point to a line is always the shortest distance to the line. Literally burn this into your memory. It serves as a massive shortcut for problem solving when you're trying to find the most efficient path in a tricky geometry question. Moving beyond simple triangles, we hit E6.3. And here, you have to be able to visually recognize, sketch, and interpret the graphs of simple trigonometric functions. You really need to know their properties intimately. Plus, this section requires you to actually solve simple trigonometric equations spanning the entire circle, so everything between 0 degrees and 360 degrees. Then we reach E6.4, and this is where the training wheels completely come off. When right angles just disappear from your problems, you're going to rely on the advanced sine and cosine rules to unlock the secrets of literally any triangle. On top of that, you need to use the formula where the area of a triangle equals 1/2 times A times B times the sine of C. And let's see how all of this builds up to the grand finale of the syllabus, E6.5. Returning to that awe-inspiring satellite view we saw earlier, the absolute peak of the syllabus requires you to solve simple trigonometrical problems in 3 dimensions. The real benchmark here? Being able to calculate the angle between a single line and an entire flat plane in 3D space. And if you can do this, you're effectively using the exact same spatial logic used to orient those massive satellites in orbit. No big deal, right? Okay, section 3, the genius of Euler, the man behind the math. Now that we know exactly what to study, I think it's vital we meet the minds who actually forged these tools in the first place. Looking at Leonhard Euler's timeline, what's truly astonishing isn't just his early fame, it's his absolutely unstoppable output. I mean, he developed the foundational ideas of giants like Newton and Leibniz, but here is the most inspiring part, for sure. Euler's dedication was so immense that he continued to produce groundbreaking calculus and trigonometry even after going completely blind. He was literally holding these incredibly complex 3D shapes and equations entirely in his mind's eye. Just wow.
So you might be wondering, how did he get famous in the first place? Well, as a young man, Euler solved a problem that had baffled literally everyone. He discovered and proved that the sum of the infinite series, so adding 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, and so on, all the way to infinity, actually equals pi squared over 6. That stunning proof of the infinite series brought the young Euler to the immediate attention of the entire global mathematical community.
But get this, Euler didn't stop at trigonometry and calculus, not even close. He pioneered entirely new fields like graph theory and functions. He found the largest known prime number of his era. He was the first to prove several major geometry theorems, studying these deep relationships between a triangle's height, its midpoint, and its circumscribing and inscribing circles. He even unlocked the volume of a tetrahedron, a triangular pyramid, in terms of its sides.
And perhaps his most visible legacy today is what I like to call the holy trinity of constants. Euler introduced the notation for pi, the constant e, and I, which represents the square root of -1. So every single time you use these vital mathematical constants in your calculations, you are directly interacting with Euler's profound historical legacy. Pretty amazing, right?
Which brings us to Section 4, the Bernoulli family drama, brilliance and betrayal. You see, Euler's story doesn't exist in a vacuum. It's actually deeply intertwined with his friends, a family of Swiss merchants known as the Bernoullis. Let's compare the two sides of their pretty wild legacy. On one hand, you have absolute scientific giants. Two brothers, Johann and Jacob, along with their children and grandchildren, were immensely gifted. They made incredible discoveries across calculus, trigonometry, probability, astronomy, magnetism, mechanics, and thermodynamics, the whole shebang. But on the other side, well, we see they were incredibly toxic relatives. The older members were notoriously jealous of each other's successes. In fact, they were so intensely competitive that they often stole the work of their own sons and grandsons just to pass those mathematical breakthroughs off as their own. It's a crazy piece of history behind the very formulas you're studying today. So as you master this IGCSE trigonometry syllabus, from those basic bearings all the way up to 3D planes, I want to leave you with this final thought. Will you conquer the math with dedication and vision like Euler, or are you going to let the pressure get to you like the Bernoullis? Use this powerful knowledge to build the future, to calculate the impossible, and to reach for those satellites. Thanks so much for joining me on this explainer, and keep exploring.